Hi there. Okay, so I've brought back our periodic table. We've talked about bonds in the last video. Don't forget, the two types of bonds that we mostly talked about were ionic bonds and covalent bonds. So let's keep up that conversation. In order to keep up the conversation, we're going to need to refer to this periodic table here and the groups that are in it. Now, there are these numbers here from 1 to 18. I don't want you to think too much about the 1 to 18 numbers because there are two ways to represent this table. In your book, it's represented as that this group here are A, or that set there are A groups, and these are also A groups. And then these D shell electrons that we talked about last time are B groups. And the B groups are a little bit complicated, so we're just not going to talk about them. Now, I mean, if you want to talk to me about them outside of the video, I'd be happy to, and you're going to see some examples of some metallic compounds in the text as you read, but I just don't want you to have to worry too much about them, okay? The principles that you learn in this video should count regardless of whether you're dealing with an occasional metallic compound or not, okay? Now, this group here is the 1A group, so I'm going to go ahead and delete these so that you can see this in terms of groups that we're going to pay most of our attention to because they're simpler. So this is the 1A, and then this one is the 2A. This group is the 3A, and it keeps just going. 4A, 5A, 6A, 7A, I'm running out of space here. And then this is the, this last column is the A group. Why do we separate these into groups? Well, as we learned in the last one, the first group here, this first column, all has the characteristic that they have one extra electron. So you can imagine that that would be the case because as you go to helium, you fill the 1s shell, and then you go back to lithium, and then you move on to the next shell. So each of these first elements in the first row all have the characteristic that you have moved up to the next level and put an electron on that level. And each of the ones in the second group, here the 2A group, have the characteristic that you have added an extra electron so that they have two valence electrons out there for the world to grab a hold of. Now, I find it useful to skip over to the 3A because later on there's all these fuzzy effects that happen with these little yellow ones down here, so we're not going to worry about those. But the 3A tend to have 3 valence electrons. 4A tend to have 4 valence electrons, and so forth, right? When we get to the group 8, then we find they're entirely filled, and recall that these are called the noble gases, so we don't actually pay that much attention to them in chemical compounds because they don't form chemical compounds. They don't have any need to. They're already happy. Recall in the last video, our two priorities for your atom are number one, that they want to have their shells filled, and number two, they want to be neutral. All of these in group 8 have already succeeded in doing that by just existing. And so they don't have to interact with other atoms in order to satisfy those demands. Now, when we look at the other groups, we can start to anticipate how they're put together based on the fact that they have this number of electrons. So each of these groups has sort of a personality, if you want to think about it in that way. It has a tendency to interact with the other groups in certain ways. This changes a little bit as you go down the chart and get into heavier and heavier elements, but by and large the groups have very similar activities. So one example of this, okay, is in the first group here, we see potassium and cesium, and there was a time when, back before we were a little bit safer with our nuclear energy, one nuclear facility actually leaked cesium as a byproduct into the fields nearby. And because potassium is something that exists in the grass that the cows would eat, and then it also carries into the milk. The problem that we had was that the cows would eat the grass, and in place of the potassium, cesium would take up the chemical spot that potassium had taken up in the grass, and so it ended up being in the milk that was distributed out from the farms that were nearby. It was really, well, let's say that it started a few rules. That tragic incident caused a few rules because cesium, although chemically it is not different than potassium in many ways, it is radioactive, and so that became an issue. So that's an example of what I mean by the fact that these are in the same group. They tend to interact with other things and fit in like Legos in a certain capacity, in the same way that all of the other members of that group try to do. Okay, exception to that rule. In this table, helium is over here. A lot of the times it's over here with the noble gases. It can be considered either a 2A or an 8A group because of it's special in that way. So we really kind of cut it off after that point to really describe the behavior on these. So let's discuss electronegativity. Okay. So I have a table here, and says electronegativity twice on there, which makes me feel like I wasted a bunch of time here writing the word. Okay, so the idea behind electronegativity is essentially this. If you're over here in let's look at our groups again real quick. If you're over here in group 8, excuse me, group 7, group 8, remember group 8's happy, we don't care about it. Group 7, we're on all the unhappy atoms. Group 7 over here, if you're group 7, remember we talked about like chlorine, and fluorine feels the same way, even more so actually. Almost has its collection complete, right? It's almost there. It just needs that one last electron, and it will do whatever it can to get it. And therefore, it's always going to end up, once it's finally semi-happy, it's going to actually end up with an extra negative electron. So in order to put itself over into that state where it's actually got all of its filled electrons, right? So what we might be able to say is, all of group 7 needs one electron, right? And then we could look at this one and say, well, how many would it take? Remember, in our lab, our oxygen atom needed 2 extra electrons in order to complete its shell, right? So it needs 2 electrons. Nitrogen needs 3. Okay, now I want you to think about this in terms of like if you go to the store to buy candy and you have $1 and you have let's say you have 95 cents and you go to the store and a candy costs $1, then you have 5 cents less than you need. And you're going to be really frustrated, right? If that's the case, then you're really identifying over here with this one that is almost there, right? You're like, oh my gosh, I'm just a nickel off of being able to buy this candy. I'm so frustrated, right? But if you walk in and you only had 80 cents, you know, then you'd be like, man, I was pretty close there, you know, not quite as unhappy. Of course, I'm completely personifying this, but it helps you to remember it. And if you're over here, and then that means you had like 65 cents, and you're like, yeah, whatever, right? I don't really. I've never had a chance of buying that candy. I'm so far away, right? If you're here, then you need 4, right? That's like having 50 cents. Okay, you're just halfway there. You're like, whatever. There's no point in even trying, right? Now think about what it's like if you're over here. If you're over here, then you have 1 electron extra. That's like having 10 cents. Or 5 cents, actually. It's like having 5 cents. So if you're someone over here has 95 cents and needs a candy bar, and there's someone over here that has 5 cents, then then this person that has 95 cents is going to be like, hey, give me your 5 cents, right? This one is going to be like having 15 cents. So they have 2 extra electrons. And so you can see how this plays out, right? That the closer you are to the right, the more greedy you are for electrons, and therefore the more negative you tend to be. And the closer you are to the left side, the more uh, excess electrons you have, and the more electrons you're willing to get rid of, and therefore the more positive you tend to end up, right? Group 8 doesn't get to be a part of this story because that's those losers that just go into the store and have $1 and buy their candy and leave, and that's not interesting. All right, so if we look at our electronegativity chart, you can kind of see what I'm talking about here. How badly do you want that candy? How badly do you need electrons, right? Fluorine is the king of this. It's up here at the top. It has the highest electronegativity because it has the highest tendency to nab electrons from other things. Oxygen's still up there too, which is actually why things burn. And then chlorine is not nearly so high as fluorine, but it's still up there, right? So what you can see here is that the smaller something is on this chart, the less electronegativity it has, and the taller it is, the more electronegativity it has. And ionic bonds only form, this is very important, ionic bonds only form between elements that are tall on the chart and elements that are small on the chart, okay? So we could have, for instance, lithium and fluorine form, and they would form so that you have a lithium, which would become a positive ion because it would donate its electron. It's 1 electron because it's in group 1, has 1 extra electron, and it would donate it to the fluorine, which would then gain the electron because it needs 1 electron, right? Okay, so this kind of bonding occurs between items on the periodic table that are far away from each other. Okay, in general, we're going to have ionic bonding between the first 2 and other elements on the chart that are higher up. Okay, so these really are the ones that tend to form ions. But we need to make a distinction between when we say the word ion in physics and when we say the word ion in terms of chemical bonds. Okay. For chemical bonds, ion has a very specific meaning. At any other time in either physics or chemistry, ion is very nonspecific. So I can have a magnesium ion, for instance, right? And when I'm talking about it in terms of physics, that could be, well, it could be a negative ion, it could be a positive ion, it could be a positive ion with a charge state of +2. It could be, in other words, I could take 1 electron off, right here, oops, right here. Or I could add an electron to it, or I could take 2 electrons off, and all kinds of stuff, right? Now, when we talk about magnesium in terms of chemical bonds, we mean one specific one of those. And what we mean is that we ask the question, how many extra electrons does magnesium have? Remember, this column has 1 extra electron, this column has 2 extra electrons. So it would mean that if we took away, if we stripped it of those 2 extra electrons, it would be in a positive 2 charge state. So that is actually what we mean in chemical bonds when we say ion. We're referring to, for chemical bonds, we're referring to an ion as magnesium plus 2. Now that's going to be important when you start looking into, which we're not going to look deep into this in this class, but if you wanted to ask the question, how would magnesium and fluorine bond together, then you would have to say, well, let's take a look. Magnesium has 2 extra electrons. Fluorine needs 1 electron. So if you dump a bunch of magnesium and fluorine into a bucket, essentially, and mix them up with a spoon, what you're going to get is that fluorine is going to steal 1 of these electrons, but you have more fluorine around. So if you have another fluorine available there, it's going to steal the other electron. So you'll have magnesium donating 2 electrons, and fluorine there's going to be 2 of them, each taking 1 of them. You will now have formed the ionic compound magnesium fluoride. Now I'm going to put a little 2 on here because when we write our compounds, we write it so that we put a little subscript on here to indicate that there are 2 of whatever the subscript is behind. We would not have magnesium 2 fluorine 2 because that indicates that there are 2 magnesiums and 2 fluorines. Okay. All right. So this then is the happy, stable ionic compound magnesium fluoride. You could guess, if someone said magnesium fluoride, you could guess what this chemical compound looks like based off of the simple fact that magnesium has 2 extra electrons and fluorine needs 1 extra electron. So you can actually just kind of piece these together like Legos, and you can actually figure out which ones the ionic compounds are. Okay. Now, covalent compounds happen between items that do not have a lot of electronegativity differences. So notice here that, for instance, carbon and sulfur and selenium are all kind of around the same level, roughly, right? Those are going to be pretty much just covalent bonds. An example of a covalent bond is diamond. Diamond is entirely made out of carbon, and so if it's just a whole bunch of carbon atoms that are connected together, since there's no difference between the electronegativity of carbon and the electronegativity of another carbon, then that means they have to be a covalent bond, which means that they equally share their electrons. It's not one carbon just throwing its electron at another carbon. They're actually sharing them. Let's take a closer look at how to name these things. So here are some examples that can help us to see how these things are named. Notice here that we end up a lot with the word "ide," or excuse me, the suffix "ide" on all of our names. That is the standard practice. So there are some more complicated versions of ionic compounds when you get, instead of having one atom that is formed with another atom, you actually get an ionic atom formed with an ionic compound, a whole other compound group, then that gets really complicated. We're not going to talk about that. I just want you to know that it's out there, and you're probably going to read it in your text too. So let's get the basic idea though. So if we just have some atoms, then we'd have to say, okay, let's look at the electronegativities of these things and find out how many how many electrons these things need, and how many electrons they're willing to give. And then the first one that we always put, notice here they have the red, the metal. We call that metal because everything, basically everything past this point is metal. Okay, everything to the left is a metal, including all of these things in group 1 and group 2 over here. So the red is going to be the metal portion of our compound, and then the nonmetals over here in this region over here are going to be the second word in your name. So we'd say if somebody said sodium fluoride, then you would know to put this. If they gave you the name sodium fluoride, then you would know, okay, I have a sodium and I have a fluorine. And I know that since sodium has one extra electron here, and fluorine needs one extra electron, they're a perfect match, and so you would just have one of each, right? If you have potassium sulfide, on the other hand, then you would say, okay, potassium has an extra electron, but sulfur needs 2 electrons. Sulfide means that there's sulfur. So if I have one of them with one available electron and one of them that is greedy for 2 electrons, then it will need 2 potassiums to satisfy the 2 electrons that it needs, and therefore you would know to write 2 potassiums and 1 sulfur for potassium sulfide. Now, if you're not given the name, you're given the chemical compound instead, like if you were given Al2O3, you would then know, well, I need to take the aluminum is the metal, and so I'm going to write aluminum as my word, and then the next one is oxygen, and so you would just, instead of saying aluminum oxygen, you would say, well, this isn't, I'm not going to call this oxygen because it's the one on the end, so I'm going to say oxide instead of oxygen. Now, some of this is really language oriented, and it just takes a little while to get used to which terms to use and to know to say oxide rather than oxygenide or oxygenide or something like that, right? So there's a little bit of a language element to chemistry that you have to just get used to looking at the compounds in your book. And when you're dealing with multiple choice, they're not going to throw oxide and oxygenide at you. They're going to give you other um, options, so it'll be a little bit easier to deal with. But so in time, you'll get it. Okay, now let's look at covalent bonds, and we've already discussed the mechanism behind covalent bonds, but let's talk about naming covalent bonds. Okay, so ionic compounds are pretty clean in that you can always know what to expect by the donations of electrons. Covalent compounds are not. They're messy, and so we have to be very careful about the way that we name them to clarify exactly what's going on with the atoms and know exactly how many atoms are doing what. In addition to the bonds being a little bit kind of hazy, the carbon atoms and some other atoms, a lot of the times, if you have 1 carbon or 2 carbons or 3 carbons, there's usually hydrogens that are present, and they can just make up the difference. And so it makes it really difficult to pinpoint what, if you can't just say carbon oxygen, because you're not sure whether you're dealing with a carbon that has 1 oxygen or a carbon that has 2 oxygens. And so in that case, we need prefixes for both or all atoms in the covalent compounds, unlike ionic compounds where you can simply just add the suffix "ide" to the end of it and it's nice and clean. In covalent compounds, we have to use the Greek prefixes. So here you may remember mono as more than just a disease. It's actually it's means a single, right? So these are, they say Greek prefix is important here, like mono, di, and tri are the ones that you're going to run into the most often. So, but you've got all of them here if you need them. The rules are you're going to have two atoms, right? Now, even though these aren't ionic compounds, we can go ahead and keep with the typical way of going about naming them by saying we generally move from the bottom left of the periodic table to the top right in our naming convention. So if you have two atoms and atom A is, let's say, phosphorus, right? And atom B is, let's say, silicon, then you're going to name this with silicon first and then phosphorus second. And the reason is because silicon is to the left of phosphorus. Also, if you had arsenic, you would name arsenic before phosphorus because it's to the bottom. Now, yeah, there's some other conventions for so silicon is to the left of arsenic and so forth, but we'll just keep them as simple as possible, okay? Some big ones that we're going to run into are you can think of like water, for instance, could be labeled as we have H2O. You're familiar with that. So we have two hydrogens and one oxygen. Now, hydrogen is all the way over on the left and oxygen is all the way over on the right. So we definitely are going to be putting hydrogen first and oxygen second. Now we use our prefixes to describe this. We would say then that water's technical name is dihydrogen. So we say have a hydrogen, we put di in front of it. And then since we have only one oxygen, we would say that that is monoxide. Okay. Now you don't have to say mono-oxide because that's already an O there. But again, there's a language element to this. You'll get a little bit used to saying monoxide instead of mono-oxide, right? So that is generally the rule that you're going to run into is you almost always put the prefix in front of the, if we have two here, you put di in front of it. If one here, you put one in front of it. The only exception is that if you have only one of the first one, then you don't put mono in front of it. And other than that, it's very consistent, okay? So for instance, if we had carbon dioxide, we would CO2. So carbon dioxide would be, instead of saying monocarbon dioxide, we would just say carbon dioxide because the first one that we label is never going to need mono in front of it. So you're never going to start off with mono, okay? That's the only exception to the rule. You never start with mono. So we would say carbon dioxide, right? And then in the case of carbon with one oxygen, we would then say carbon. Now, since we only have one oxygen and that oxygen is not the first element, we would need the monoxide. Okay? Now here are some more examples. So here are some examples. We can see that with one sulfur and two oxygens, that would be named sulfur because it's not monosulfur, remember, because it's the first element and there's only one of them. And so we would say sulfur as the first part. And then since there are two oxygens, then we'd say that's oxide, but it's 2 oxygens, so it's dioxide. The second one that we have here is not NO, it's N2O. Now, since we have more than one nitrogen, we need to clarify that there is more than one nitrogen by putting di in front of it. And then since we only have one oxygen, we put mono in front of it. And we put mono in front of it because it's not the first one, it's the second one. And there's only one of them. So you can start to see the pattern here, where with carbon tetrachloride, you have carbon is only has one, and it's the first one, so we don't need to put any prefix. Tetra tells us that there are 4 chlorines. So when you see these names, you should be able to write the chemical symbols. Oh, sorry about that. Okay, let's, my screen was giving me lots of trouble here, so let's give you an example that you can try. I'm going to write out diphosphorus pentoxide. And I want you to pause the video and imagine what you would write the chemical symbol as using the rules that we've already listed. Okay, now if you've paused the video, then hopefully you will have recognized the prefix di and the prefix pent, which is short for penta, right? So then that would be 2 phosphorus. We have two phosphorus atoms, which notice here on the periodic table is listed as P, and then 5 oxygen atoms, so we would list that as P2O5. That would be your answer for diphosphorus pentoxide. Another example would be if I were to give you NO, NO, okay? And then you need to determine what the chemical name would be for this. Pause the video. Try it out. Okay. Now, we would recognize that there is one of each of these atoms, nitrogen and oxygen. The first one is nitrogen, and instead of dinitrogen like we had up here, since we only have one, we need to be careful not to label it dinitrogen. We also need to be careful not to label it mononitrogen, because it's the first one, and you never start off your chemical name with mono. So you would say simply nitrogen monoxide. Okay, hopefully at this point you're getting the hang of it. Practicing the problems in the book will help, and this closes our video on differentiating between ionic compounds and covalent compounds and being able to name